Okay, so on this proof, what we're doing is we're asked to find that RZ is equal to TZ. And though this is a triangle, we're showing you how the fact that it's a triangle actually doesn't come into play when doing this proof. Instead, it's all about segments, so we need to show they're congruent. Whenever you show that segments are congruent, a common way to do it is to use segment addition in some way. So we start by just writing out our given statement in a traditional two-column proof method. So we're going to start with RQ equals TP and ZQ equals ZP. And our reason for that is going to be given. That's the information that we're given to you. You're told that RQ equals TP and ZQ equals ZP. Now, if we go look at that, that means that this is congruent to that. That's the ZQ congruent to ZP. And then we're told that RQ from R to Q is congruent to P to T. Using logic, it's pretty easy to see that RZ and ZT would be the same. That's not a hard thing to see, so we just have to go through and prove it. And the way that we prove it is using segment addition. So we start by defining the two segments that are there. So we can either do these two segments or these two segments, but it obviously makes sense to do RQ and TP because they're the longer segments. So we could say PZ plus ZT equals PT. That is by segment addition. Now notice that means the length of PZ plus the length of ZT equals the length of PT, not the segments themselves. In this same step, we can do the other segment addition. We don't need to do two steps for this. We can just do RZ plus ZQ equals RQ. And so now we've got these two statements using segment addition that are going to be very valuable to us. They're valuable to us because we know that these two are equal to each other. So we can take those two and substitute them into this equation here to get, well, instead of TP, we're going to do PZ plus ZT. And instead of RQ, we're going to do RZ plus ZQ. Now this is because of the substitution property of equality. Notice we're substituting in lengths, not actual segments. You can't substitute segments, only their lengths. And so we want to go through and then look at this statement we just created. PZ plus ZT equals RZ plus ZQ. Now, if you notice, our goal is to show that RZ and TZ are equal. Well, here they are. They're on the same opposite sides of an equation, which means that PZ and ZQ need to cancel each other out. And that happens through one more substitution of recognizing that PZ is just the same as ZQ. So now, on both sides of our equations, we have a ZQ, and then the two things we want to set equal. So we can subtract those away by the subtraction property of equality. So the ZQ and the ZQ are going to subtract away. In the proofs I do, I don't go into the detail in the algebra. I allow my students to skip the algebra step and just to claim that ZT equals RZ. I make the assumption that you know how to do algebra. And so that's the subtraction property of equality. And that's your proof. You're done. If they needed to prove them congruent, you could have done that in one more step by definition of congruence. But otherwise, that's a pretty simple proof of showing ZT equal to RZ.